Good morning, mathematicians. Late stream today. Because I had other stuff to do. Because I did have other stuff to do earlier in the day. And now we're here. Good morning, mathematicians. Oh, I don't even have my microphone. I shouldn't have started the stream today without my microphone. That was a bad move. But I will remember to jump to live chat right away. So there's that, at least. Good afternoon. Yeah, basically, almost 9:46 in the afternoon. There was a song about that back. You kids probably won't remember the song "Dying in the Afternoon" because I'm an old dinosaur, and that was from the emo days of yore. But the real ones will remember. The old geezers like me will remember that one, undoubtedly. But don't worry, I got my microphone, so we'll get set up here. Probably not going to go very long today. I mean, we haven't been lately, in general, but especially not today. Yeah. But what will we do today? That is the question. Maybe we could compute. What did I say yesterday? You listen exclusively to ancient Sumerian hymns. Oh. Well, not exclusively, because you're listening to me. I listen to exclusively future music that comes through a time portal. You told yourself to stop playing video games when you get the notification and completely lost track of time. Yeah. Well, I guess that's partly on me for starting so late. I made you play too many video games. Yeah. Okay, let's see. What were we talking about? Yesterday? I mean, I finished up with these computations of different extensions of E8. E8. What the hell am I talking about? The quaternions. Good morning, Ken. Hope your quals went well. Yeah. I guess we could just learn some Galois cohomology tomorrow. The notification is dinner reminder for you. Well, time to bulk up on some dinner. Let's just read some Galois cohomology notes, shall we? William Stein, why not? Let's start here. Let's just read some Galois cohomology together. That'll make everyone happy, right? This will be entertaining, right? Right, guys? You guys will like my videos if I do this, right? I better get 1,000 views on this video today. Yeah. As we all know, number theory is the study of this group. This is true. This is literally all of number theory. This problem from your qual stumped you. Let G be a group of order 4m where 4 is odd and G has order 4. Little g is an element of order 4. Prove that any h of order 4 is conjugate to G or G inverse. And then show that G is not conjugate to G inverse. Yeah, I almost wonder, should I have a separate stream? I don't have time to be doing that. But Yeah, it could be a good idea to have a separate stream where I like suffer through something, like Galois, called like suffering through Galois cohomology. Let me plug my writing thing in here. I'm a disorganized mess today, I guess. Math snuff films. There's a market for that. Yeah, like, I mean, technically, like 2 people is a market, right? Maybe there's like 3 people out there. I doubt it. Or maybe there's more. Who knows? Who knows? Hello, Fimno. Okay, so let's see. G has order 4M. G has order 4M, where M is odd. And G is an element of order 4. So, right. Basically, there's like 2 conjugacy classes. There's 2 conjugacy classes of elements. So H is order 4, then H is in the conjugacy class of G. Isn't it just CELO? Well, what do you mean by that, Femno? Tell me the rigorous proof. I mean, like, definitely the screams applied the CELO theorems, but, okay, like, what's the proof? Yeah. So, I mean, I guess we're trying to basically count conjugacy classes of elements of order 4. So I'm tempted to use the class formula here, actually. So, I mean, what does CELO tell us? Yeah, so I guess CELO tells us the number. I guess CELO tells us the number of... right, if we use CELO 3, so the number of 2 CELO subgroups, it says that G and H are conjugate at least, right? Right, CELO does say that G and H are conjugate, and so I think that's equivalent. Yeah, the subgroups are conjugate. I think that should be equivalent to G and H being conjugate. What is a generator of a group and a subgroup of a cyclic group? Well, a generator of a group, I mean, so, like, for example, the dihedral groups, right? So this has 2n elements in it, and what is it? It's the group of all isometries of like a polygon, right? And so, okay, yes, the entire group has 2n things, but much like how a basis in it, so a vector space has infinitely many elements of, oh, well, if we're over an infinite field, it could have infinitely many elements, right? A real vector space. But you can always write them in terms of some combination of a finite list of things, right? If it's a finite dimensional vector space, right? That's what a basis is. Generators for a group are the same thing. So, for example, every element of the dihedral group can actually be written as just some combination of, you pick one of the rotations and one of the reflections, and then every single element of that group you can write just in terms of that one reflection and that one rotation in some combination. Yes, it definitely... right. Yes, exactly. That's true. Right. Okay. Yeah. So yeah, G... So let's say they're conjugate by this, right? So in particular, that means that K inverse should be equal to h to the m for some m, right? So I guess we just want it to be, we just want it to not be h2, right? But that makes sense, right? Because if it were conjugate to h2, then that means that gk squared would be h2 squared. I mean the order of h squared is 2, right? And that would mean that the order of kg inverse is 2, but that's a contradiction. We know that the order is just going to be the order of g, which we're already saying is 4. We're choosing a generator, so it can't be 2. So it has to be h1 or h3, but h3 is h inverse. Sorry, it's extremely smoky because the world's on fire. Yeah. Fields medalist behavior. Yeah. Not writing down the details. Yeah. Yeah. Big Fields medal energy for sure. Okay. Let's go back to Galois cohomology. Show that G is not conjugate to G inverse. Right. Show that G is not conjugate to G inverse. Well, suppose it were. Good old proof by contradiction. Suppose that it were. I don't know. What could we do? Right. I don't know, actually. Suppose it were G and G inverse in the same conjugacy class. Do we want the class formula here maybe somehow? All elements of order 4 are conjugate to each other. Maybe you can say something about size of conjugacy classes. Yeah, we might want to bring in the class formula here. Wait. Hang on. Right. Well, it's not true that all elements oh, right. Sorry. Yes. Right. You're right. So if this were true, then all elements of order 4 would be conjugate to each other. Right. So I guess we could say something like G acting on the set of elements of order 4 we have a transitive G action. And so by orbit stabilizer, this is the size of the orbit times the size of the stabilizer. This is 4m. This is, I guess, do we know? We don't know necessarily how many elements of order 4 there are in total. Maybe I'll stay agnostic about that for a second. What about the stabilizer of an element of G? Of an element of order 4. It's just different notation for the same thing. Well, definitely, I mean, what's gonna stabilize G? It can't be the whole, I mean, the orbit, this thing can't be trivial, right? So otherwise all elements would have order 4. Can we rule that out as a possibility? I mean, I guess we're assuming M is non-trivial. I need to be more precise about this, but you know, I'm pretty sure we could rule that out as a possibility. And so this would have to be some subgroup. Yeah, what about the elements in this, right? I guess if we had, right, the powers of G itself, right, those all fix G, so then this has order at least 4. Can it have order greater than 4? I mean, a priori, this should be right. The order of O has to be divisible by 2 at least once. Why? The order of 2 has to be divisible... The order of O has to be divisible by 2 at least once? Why do you say that? So the order of the stabilizer can't be divisible by 4? But why? Oh, because the elements of order 4 come in inverse pairs. Do they come in inverse pairs or general? What was the phrasing of the question? Right. Oh, sorry. Yeah, the elements of order 4, right. They do come in inverse pairs. Right. 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 So it does have to be... Right. So maybe that is already our contradiction then. Because the centralizer group should be divisible by 4. Yes, and the orbit should be divisible by 2. So we have a contradiction because there's too many factors of 2 on the right hand side. Nice. Nice. I think that does it. Yeah. Okay. Time for Galois cohomology. Study the group by studying its cohomology. We can also find all extensions, as we know. Don't see why the stabilizer is divisible by 4. Well, because it should contain the cyclic subgroup generated by G, right? Right? Because like any power of G, if you conjugate by any power of G, you'll just get G. Right, yeah, exactly. Or you can also say it that way. This is just the first thing that came up when I googled Galois cohomology. It's William Stein. William Stein's notes. G modules, dimension shifting. I love. It's also in. I've got Brown's cohomology of groups. I just love how dimension shifting really sounds like some like nonsense new age whatever. Yeah. Yeah. It's just a whole bunch of cool theorems that we're gonna cover. Okay. Let's move on. G modules. We all know what a G module is, right, gang? Suppose we got any group, an abelian group that it acts on. Linearly, I guess we could say, well, this is equivalent to giving a ZG module. Lambda, I guess we'll call it lambda here. Call mod G's an abelian category. We got exact sequences. We got our fixed points. Boom, fixed points is a functor. Famously not exact functor. But it is left exact. Nice. Wow, we're flying through this. Group cohomology is so easy, guys. Yeah, maybe this will be the start of a saga for office hours. I'll let myself get distracted. You know, by other viewer questions, but this will be the beginning of the saga. So maybe I'll bookmark this tab. Yeah. And I'll go at the speed that makes sense to me. Which means some of you will be left behind in the dust, and others will be laughing at what an idiot I truly am. And be shocked that, you know, I'll probably be a doctor of mathematics soon. Presumably. Office hours, Galois cohomology read along, baby! Yeah. Okay, a covariant functor. Yeah, we got it. Yeah, exact. Yeah, we got it. We got projective modules. We got injective modules. A is induced if for some abelian group. So as a module, if it comes from just tensoring some abelian group. Interesting. Just some subgroup? It doesn't have to be a submodule? Wait, tensored over by Z? Okay. Interesting. And it's co-induced if it's the Hom set. Okay. Okay. I mean, I guess technically, you could view it as like extension or restriction of scalars of ZG, where ZG has the trivial action. Yeah. If G is a finite group, then I guess we're missing X there via this isomorphism. That's what happens when we read random notes instead of a textbook. I think they're taking here modules in the sense of ZG, not over any coefficient rings. So modules equals abelian groups. But what do you mean modules equals abelian groups? I mean, yeah, modules should mean in the ZG sense. But that's not, I mean, an abelian group A ZG module is more structured than just an abelian group, right? Well, let's just trudge ahead and see what happens. Every module is a quotient of an induced module. So let A naught be the group. You meant when you asked if it's a subgroup or a submodule. Oh, I see. Right. Yeah, I think in that case it's just a subgroup. It's just a subgroup. But maybe I'm wrong. I guess things will become clear as we press on, I think. So every G module is a quotient of an induced module. If we let A being the underlying A. Yeah, I mean, already this is confusing because this should just be the Z tensor product. No. Oh, yes, maybe it should be. Then we have this. And then thus we have this isomorphism. Okay, let's write this out. So lambda is, so we have lambda. This is the wait. Yeah, okay, so we have A. So we have lambda is this. So we have ZG is acting on A. Let A naught be the underlying abelian group. This is the adjunctions co-unit. That I believe that. But I want to write it out. So then we have ZG ZG over Z tensor A naught. So should surject onto A. Right, of course, right. Yeah. And the map sends an element, I don't know, what should I call this? Alpha tensor A to alpha dot A. Sure, okay. Right, I guess that's the the adjunction of like taking underlying abelian groups and then the induction from abelian groups. Yeah. Then we got our derived functors. We have a uniqueness, is the unique functor theorem. This is the unique delta functor whose H0 is AG, and such that if A is injective, then all of these are 0. That is interesting. Why is that true? Hello, Lola. I think I am going to hang up soon, though, so I have to do some work. The question is this, though. It's smoky outside. Actually, let's see. Air quality, Calgary. Do I do a jog outside, or do I, take a bus all the way to campus to run inside? Only out of 4. That's not bad. I'll just stay home and run from home. That's what I'll do. Semester started, so you missed a week of streams. Well, the beautiful thing is it's the weekend, so you can spend your whole weekend ignoring your homework and watching the recorded live streams. That's what weekends are for, baby. Yeah. Okay. Why is this? Okay. Thus, everything we prove about the functor must follow from the properties above. Why is this true? Can we prove this? Is it a waste of time to prove it, or should we jump ahead to more interesting things? I don't know. But so HQGA claim is this is the unique delta functor. Unique delta functor. Yeah, office hours speed run. Start from office hours 1 and work your way up. If A is injective, then HQA. I might even start titling this something else. Yeah, I might. You know what? Yeah, officially, I'm going to change the name from office hours to Galois cohomology SAGA. And I'm going to start saving these in a new playlist. That's what it is. What's the exact definition of delta functor and morphisms between it? Because maybe we can prove it from here. Cohomological delta functor is a family of covariant additive functors together with those morphisms. Yeah. Which induce a long exact sequence. I see, and then right, those are morphisms, are these induced squares. Yeah, so I wonder. There's got to be a general property of delta functors that we could use to prove this, right? I mean, I guess it's because of the fact that so what's part of the claim? Is that if A is injective, I mean, of course we know that these things are true, but why is this the unique functor that does this actually? So suppose F, I don't know, gang, you should vote if we should spend our time on this result or just take it as given and go to the more interesting Galois cohomology. So suppose F is delta functor, and maybe I'll call it F dot. Where F0 of if they agree on injective resolutions. Yeah, I was thinking we'd use the injective resolution part. Yeah, I was thinking they'd agree on the injective resolution part. But it's interesting, like, I wonder, maybe do we also need to apply this part somewhere to get some, like, normalization? Yeah. So F0G is this. And then F0, what am I trying to say? Or sorry, F0, right. Let me call this, sorry, I should call this A. And the right. They agree on all injective resolutions. They agree on all injective resolutions. Yeah, so does it actually just follows from 2 then? Oh. Well, I think we'll leave it. I think we'll leave it here. We may come back to delta functors tomorrow. But so begins the Galois cohomology saga. I'll see you all tomorrow. So many smiling faces streaming in. I love to see it. Unless you're laughing at me, then I still love to see it. Okay.